Okay, welcome back everyone. I hope everyone is already here in the Zoom session. Great to see you all. We are in NordicSMC conference and now we are on session 2, sound design with myself, Adrian Latupeirisa from KTH in Sweden. So before we start with the presentations, I will just go through the order of how this session is going to be structured. First, all 4 presentations videos will be played back to back. And then during the presentations, during the videos, feel free to use the Q&A function here in Zoom to ask your questions. Don't forget to specify to whom the questions are addressed. If you forget the names, you can also use just to paper 1, paper 2, paper 3, or paper 4. And then towards the end, we will have a discussion together with all of the presenters. And the whole sessions will run up to 1 hour. So the presentations that we are going to see in the sessions are paper 1, Investigating the Sound Design Process by Rod Selfridge and Sandra Pauletto from KTH. Paper 2, From Foley Professional Practice to Sonic Interaction Design, Initial Research Conducted within the Radio Sound Studio Project, with the short title being the Radio Sound Studio Project, by Sandra Pauletto, Rod Selfridge, Andre Hopsapfel, they are from KTH in Sweden, and Henrik Frisk from KMH, also in Sweden. Paper 3, Analysis of Concatenative Synthesis Techniques by Kura Parkola and Vili Visakorpi and Alec Wright from Aalto University in Finland. And paper 4 is Design Approaches to Alert Sounds for Interactions in Shops by Puspita Parahita Anindita and Shetil Falkenberry from KTH in Sweden. Okay, so without further ado, we are going to watch all of the 4 presentations.
Hello, and thank you for inviting us along today to speak about our paper, Investigating the Sound Design Process. My name is Rod Selfridge and co-author is Sandra Pauletto. So we're looking to investigate a novel method for eliciting information about the sound creative processes. Doing this by interviewing and speaking to sound designers in media production. These could be Foley artists, people working in game audio, radio, film, TV, etc. And we're looking to connect sonic interaction design with existing sound design practices. So product designers often have to give digital objects meaningful audio feedback, and this is a part of a wider project to inform and develop new techniques and new tools for implementing sounds of these new digital objects. So sonic interaction design is described as practice and inquiry into the roles that sound may play between users and artifacts, services, or environments, in applications that range from the critical functionality of an alarm to the artistic significance of a musical creation. Now, the creative design process happens in action while the designer is doing whatever it is they're doing. So there's 2 methods of studying this. Is in the studio, which is great for an ethnographic study, but it's difficult to generalize between practitioners. And then the laboratory, which is better for generalization, but this generalization might not transfer to real life settings. Now, for this process, we used ethnographic techniques. We didn't have time to do a full ethnographic sort of study, the months that take. But we do use techniques of video recording, audio notes, semi-structured and informal interviews, observations, etc. We also use the think aloud technique, which is a proven method for revealing knowledge from participants engaged in an active task. And participants speak their thoughts with minimal interruptions from the researchers. So the complete study we designed to elicit this information is a combination of in the studio and laboratory. It goes over 4 days. So the first day is initial, just meeting up, building rapport, finding out about the work that the sound designer does, as well as explaining our research. In the second meeting, we observe sort of moment by moment, watch them work, sort of find out how they operate, what tools they use, these sort of things. And then the third day, we observe how they approach a given brief that's been designed by us, which we give to everyone in the study. Then the final day is observations, where we clarify things. They have a chance to ask questions, obviously. We find out about their background, their education, and things like how they see themselves in the wider design process, their roles. So focusing on the design briefs in particular, they're influenced by design thinking with the sort of steps of empathizing, redefining, ideating, prototyping, and testing. We added a number of what-if questions in there to stimulate further discussion. So the first task was an abstract brief where we asked the participant to choose a two-dimensional shape and then asked them to make the sound of it walking happily down the road. This sort of challenges their habits, but also gives them practice at speaking out loud, which doesn't come naturally to some people. The listener in focus was the second brief. And this is more to investigate how the sound designer considers the listener by asking them to create the sound of a thinking, active brain to be listened to by engineers. And once they've come to the end of that process, we change the listeners to vegan. Now, obviously, engineers and vegans are not mutually exclusive. One can be both an engineer and a vegan. But that's the point. The sound designers then can choose if it's appropriate to change or if they want to keep the sound the same. It's their decision. But we're interested to see what they do based on the sort of their characteristics of the audience that has been highlighted to them. And then the third one is a case study, the sound of air pollution. We asked them to make the sound of a coat that measures air quality and communicates that sonically to the wearer as they move through changing areas of pollution. This is a sonic interaction design task, basically. So our focus is to evaluate whether the briefs stimulate creative thinking. We had two participants for the pilot. Participant A, who was a professional who worked within game audio studios, and participant B, who worked within Sonic Arts and games, often on solo projects. We did a thematic study of the comments that the transcriptions basically from their design processes. And you can see we came up with a number of themes, which are highlighted here on the right. We did a bottom-up thematic study, so the themes were identified from the data themselves. And then we also realized that these themes, a number of them, match up with other themes that have been found by Cash and Storga in their research in the Journal of Engineering Design, where they performed similar tasks. And I highlight again, it's not the goal to analyze the sketches that the sound designers come up, it's the process of whether their briefs have come up with stimulated creative thinking. So if we look at the results for the abstract brief, we can see that participant A draws on association and scene ideation through his process, while participant B has a lot of ideation and a lot of reflection. We also see that participant B brings in a lot of personal background, while participant A here considers the listener in the first task. When we move to the second one, listener in focus, we can see that both participants progress through a lot of ideation and a lot of reflection, although there's a much more reflection in participant B and much more sort of ideation with participant A. And both the designers, when considering the listener, changed their designs when the listener changed. And the final one was the case study. We can see from the results from participant A that there's a lot of ideation, but there's also scene ideation, decision-making, reflection, roughly in equal amounts, while participant B is really a lot of ideation and a lot of reflection. within the comments that they made throughout their process. It's also important to do some reflection on the researchers ourselves as our comments through the tests. So we did a thematic analysis of our comments and came up with these 5. So flow breaking, leading the participant, reinforcing the participant, unnecessary feedback, the sort of more negative contributions from the researchers. Vocal encouragements are permitted through the Think Aloud technique and generally required if the participant is silent for any length of time. And we can see that through test B with participant B, we've got much less negative comments, but there was also less vocal encouragements required. So in our discussion, we can see that participant A's process drew a lot from associations and personal background, while participant B has significantly more reflection than participant A. Participant B considered a listener early in his design process, and this is believed possible due to him working on solo projects more than being part of a design team. So he tended to think of the listener, have much more connection with the listener, with the end user. And this is possibly reinforced by the fact that he made much more use of vocal sketches as well, possibly again due to having to communicate with the end listener who maybe doesn't have the same vocabulary as somebody who's working in the studio. The abstract brief was successful at facilitating Think Aloud, but also allowed the participants to understand the scope of their control and what decisions they could make. The listener and focus brief, both participants changed their design in relation to the target audience, which was interesting. And the case study, The Sound of Air Pollution, it really magnified the difference in their approaches, as participant A focused really on developing a specific sound, while participant B focused on creating a system that would create a sound rather than the sound itself. So in conclusion, the method has allowed us to elicit participants' design processes. We're able to compare participants. We're able to derive a number of themes, and these themes appear to be comprehensive. Thank you, and happy to answer any questions at the end of this session.
Hi, and welcome to this presentation. My name is Sandra Pauletto, and I will present the paper From Foley Professional Practice to Sonic Interaction Design, initial research conducted within the Radio Sound Studio project. The authors are myself, Rod Selfridge, Andrea Olzapfel, and Eric Frisk. The Radio Sound Studio project, which is funded by the Navet Center of the Royal Institute of Technology in Stockholm, aims to develop novel sound design tools which are informed by digital models of historical sound effects. It aims to provide a tangible approach to connecting new sound design developments with historical literature and practice. The project combines methods from sound computing, ethnography, and design research. The tools developed will address both artistic sound practices and more utilitarian sonic interaction design for new digital objects. Additionally, we aim to formalize the digitalization process in order to inform how digital archives of sound objects and practices could be developed, creating new opportunities for radio, TV, and Foley studios. Sound design research is in its infancy when compared to music or speech research. Key to its advancement is an increased understanding and connection with current and historical practices, which are mainly situated in media production, radio, TV, and film. In particular, Foley creative practice provides ways to investigate sound production and perception from ecological and enactive standpoints. Two main aspects are particularly amenable to sonic interaction design. First, Foley sound design is often based on acoustic modeling rather than the attempt to reproduce natural processes. Secondly, a number of often simple gestures are coupled to the production of different sound outputs. The digital sound models developed in this project will be investigated and expanded through workshops inspired by the NIME research and design research. In this article, we describe the initial research carried out in this project, which included a semi-structured interview with Swedish radio sound engineer and sound maker Michael Johansson, observation of sound design practice, the selection of 3 sounding objects, which will be the focus of the project, and the initial digital modeling of one of the objects using procedural audio and physical modeling in pure data. Here is a summary of the main information derived from the interview and practice observation. In regard to production workflow, Michael mentioned that he would record the voices first in the presence of the director. This confirms research by the first author, which found the voice is prioritized in other media productions, such as film and television, both in terms of time and in terms of director presence. Similarly, the production of the rest of the sound design is left to the sound professional's creativity, with the director providing feedback only after an initial sound design has been produced. Michael said, in relation to the making of the radio play Turid, a Viking saga, "Mostly I did it based on my own experience, what I feel. If there is something missing, I had to feel like I'm following her, the character." On ideation, Michael said that ideas often come when he's outside the studio and in movement. Usually, I do that on my way to work or on my way from work. So I have got some ideas when I am in here. The most important goal in sound design for radio, aside from providing a context and a scenario, is to create a sense of presence, to give a body to the voices. In particular, sounds are used to give a sense of body movement. Michael says, "I kind of get the tempo and the feeling in the movement from hearing the voices first. That's how I work. Maybe I do a movement 10 or 15 times until I feel I got the perfect movement." 3 sounding objects were selected for this project. The first 2 were utilized in the radio play Turid, a Viking saga. In this play, Turid is a 15-year-old royal daughter who is forced to embark on a life-threatening journey. The first object is a wooden spoon wrapped on wet cloth. Turid needs to make a sacrifice to the gods, and that's represented by spreading butter on a holy rock. Michael researched what kind of utensils Vikings were likely to use, and he came to the conclusion that a wooden spoon might be a realistic choice. He then tried to rub the wooden spoon against rocks, but soon realized that the sound was too hard. So to model the butter, he covered the spoon with a wet cloth. 2 aspects were particularly interesting for our project. Firstly, this is an example where the sounding objects are completely mundane. And secondly, they portray something quite different from their normal use. They're used as a substitution of something highly specific to this story. So the creativity of this substitution is what is interesting for us. And we wonder whether it could be expanded to portray other feelings or other situations. Here is an example of this sound. The second object we selected was a pair of old Swedish clogs. We selected this sounding object not for its typical use, which would be footsteps, but for its capacity to portray bodily presence and for its implicit cultural and geographical references, as Swedish clogs are different from other types of clogs. Michael said in relation to the clogs, "The sounds I had to make are usually sounds that give a body to the characters, what they are saying, what they are doing. So that's the purpose. You can feel that the voice has a body. That's what I'm trying to get to create. Even when the characters are supposed to be simply standing in a Viking house, a slight movement of the clogs on a surface and subtle sounds of clog-to-clog contact will provide a body to the voice." The final object we selected was called a Squeaky Box. This is a purposely made sound machine that produces squeaks and creaks when one rotates one or both the handles. It has been used in many plays to portray a creaking floorboard or a squeaky handle, etc. We selected this object because it is an example of acoustic sound model. It presents the performer with some explicit affordances. However, as it is not an everyday object with a given function in real life, it might provide the performer with additional possibilities for creation. You cannot see it in this video, but there is another similar handle on the other side of the box. At the time of writing this article, we have developed an initial modeling of the squeaky box. Here is an example of the sound. This first implementation uses the friction object from the sound design toolkit to stimulate the rubbing between the handle wood and the box surface. In addition, it uses a modified version of the creaking door model by Andy Farnell to create the creaks and aspects of the squeaks. More details about the parameters can be found in the article. Plans for modeling the spoon, including using the friction model with filtering to model the wet cloth, while for the clogs we are intending to modify existing models of footsteps on surfaces with the addition of impact sounds to simulate the clog-to-clog impacts. We have described the initial stages of the Radio Sound Studio project. We are now refining the digital models and running acoustic comparisons between the digital and the acoustic models to ensure that they are relatively similar. We are also running pilot studies with students to evaluate the performability of the digital models when coupled with simple gestures. Here in the image, you can see some simple interfaces we have developed to play with the digital models of the Squeaky Box. We have run an ideation workshop at the Royal College of Music to develop new, different kind of interfaces for the sound models. And these new interfaces will be used in a workshop with the general public at the Tekniska Museum in Stockholm. We also have plans to formalize the digitalization process in order to inform the development of digital archives of sounding objects and sound design practices. Thank you very much for listening.
Hi, my name is Kuuro Parkkola. I'm a master's student at Aalto University, and I'm presenting work I did based on a school project I did together with Vili Visakorpi. We were supervised by doctoral candidate Alec Wright. The school project was originally about trying a few different concatenative synthesis approaches, and the paper is about finding applications for these approaches. In this presentation, we will first go through an introduction, then we'll take a closer look at the techniques, then we'll cover the general anatomy of sound textures, and finally we'll go through findings and conclusions. So, in general, concatenative synthesis is about using a small amount of source audio to generate a stream of arbitrary length. We can do this through different types of looping techniques, but we need to take into account that the human ear is very good at noticing repetition and patterns. These techniques are used a lot in, for example, video games, where the length of a level is defined by how fast a player can play through it. The first technique is simply looping the source audio, so playing it over and over again. This is very easy to implement and very trivial, but it doesn't even try to mask any repetitions. To mask repetitions, we can then take this a step further with randomized windows. So we can select a random starting position and length for each window and concatenate these to create the stream. And this, however, doesn't take into account sudden or changes over time in the timbre of the source material. For this, we need descriptor controls. So we can split the source audio into small sections called atoms and map each atom according to a set of acoustic descriptors. This ensures that we can group the atoms such that consecutive atoms in the stream are not too different from each other. For this paper, a new approach or an extension to the CSDC approach was implemented where descriptors were computed for the beginning and the end of each atom, so that we can use longer atoms where the timbral content of the atom can change over time. So we can still create a natural flow in the timbre. Now to the anatomy of sound textures. So we can in general categorize sound textures into 4 groups, and noisy or static textures, which doesn't really fit into any of these 4 categories. The 4 categories are impulsive, time-varying sounds, like the crackling of a fireplace. They can be smooth and time-varying sources, like traffic noise with cars passing by. And we can have impulsive and repetitive textures, such as machinery, and smooth and repetitive textures, such as a ventilator, where we have a clear pulse, but the sound events are quite long. So now we can go to the findings and find algorithms and parameters so that we can synthesize each of the previously mentioned types of sound textures. The analysis is done based on spectrograms to visually view artifacts and the similarity between original sources and synthesized streams. Also, these have been evaluated audibly by listening for audible artifacts. First, for the static textures, here we have heavy rain synthesized. We noticed that randomized windows and looping are very good ways to synthesize these noisy textures. Random windows can produce the texture with less source material, but our implementation was not perfect, so we still have some phase artifacts left. Repetitive textures are quite easy to implement with the looping technique. However, we need to synchronize the length of the loop to the period of the source material, and then we can create nearly indistinguishable results. For time-varying and smooth textures, these are the most difficult to reproduce because here we have long time events that span over multiple atoms. So to create a smooth flow in timbre, we need to use the CSDC approach. Especially the CSDCE, or the extended version, seems to work pretty well. Although we still have some timbral jumps left behind by the algorithm. For time-varying and impulsive textures, we can use the randomized windows, because here a single time event, for example, a crackle of a fireplace, does fit inside a single atom. So when we're concatenating these atoms randomly, also these time events will be randomly present in the output. So finally, we can actually reproduce most sound textures with these very trivial techniques. And actually most of the ones that we can reproduce as a mixture of multiple streams. So for example, we can have background noise, static noise synthesized with the randomized Windows technique, and we can add some sort of machine on top of it using the looping technique, and then we can add additional sound events as pre-recorded samples. And actually this is what's often used in video games. These approaches covered here are not very recent, so the newest ones are actually about a decade ago. But still they do find practical solutions or practical applications because of their simplicity. So they are very suitable for low-budget indie-style games, for example, where more up-to-date and modern approaches might be too heavy and too hard to implement to be practical. I thank you for your time.
Shoplifting is a serious issue. It causes loss, which could be avoided if one could deter the shoplifters. Surveillance, threat of being observed, and the store's design and layout are some of the primary deterrents. If we consider the soundscape of a store as an element of its design, then maybe we could use it too. The background music of a store could influence visitors' behavior, such as movement pace, product choice, and perceived quality. But can we use it to influence shoplifters' behavior too? If we mix subtle sound alerts to the background music, would the visitors felt observed? In this research, we focus on the sound design that targets attention of people to the changes in the background music. We try to identify some design strategies, and in a scenario where the sound are mapped to the visitor's action, we try to find the preferable design. 8 participants watch a short first point-of-view video of a clothing store interior, where the person walked around and lifted the jacket and hung it back. They were then given 3 background music tracks. The background music consisted of instrumental electronic pop music usually played in a fashion retail store. Background music 1 and 2 have a pulsating rhythmic instrument playing in a constant beat, and background music 3 consisted of only ambient sound. Additionally, they were also given 1 store soundscape track. Then, they created sound alert matching the video scenario. Then afterwards, submitted the alert, already mixed with the background music and the store soundscape, along with the documentation of their design. Afterwards, they evaluated the sounds. This was anonymized and randomized. The participants were asked if the sound fits the criteria with a yes or no. The criteria are noticeable, blatant, disturbing, fits the background music, fits the environment, and related to action. They were also asked to pick the best design for each background music. And finally, they had to describe the sound with 3 to 5 adjectives. From the design documentation, we synthesized three main design strategies. Altering, which includes changing the background music itself, for example, by distorting the sound or adding a filter. Overlaying, which includes adding an alert sound on top of the music and mixing them. Altering overlaying, which combines altering and overlaying, usually altering the music through a filter and adding another sound on top of it. Two participants stated how they attempted to match the sound with the action through pitch increase, panning, and the symbolic sound of a clattering hanger. With background music or BGM1, the highest scoring sounds are sound design or SD1 and 4. BGM2 is SD2 and BGM3 is SD5. SD1 and SD4 has the highest score in general. With BGM1, SD1 and SD3 have the most votes, while SD1 also has the highest score. SD3 scored below average. With BGM2, SD2 and SD3 have the most votes. SD2 has the highest score, but just like the previous case, SD3 also scored below average. Finally, with BGM3, SD4, SD5, and SD7 have the most votes. SD5 has the highest score, and SD4's score was above average. However, SD7 has the lowest score, but still have most votes. This shows that the score itself is not a reliable predictor of votes for best design. The sounds that have more best vote on BGM1 and 2 tends to have altering strategy. And the sounds that have more best vote on BGM3 tends to have overlaying strategy. Now, let's hear some samples of the design, shall we? This is BGM1 mixed with Sound 1, which was voted best and has highest score for BGM1. And this is the design cropped from the rest of the BGM. Now is BGM2 mixed with Sound 3, which was voted best but scored below average. And this is the cropped version. Finally, we have BGM3 mixed with Sound 7, which was voted best, although had the lowest score. And this is the cropped version. What do we learn from this study? First, it was observed that there is a preference for simpler alert, for example, pitch bend or just a single note. And we could categorize the result into three design approach: altering, overlaying, and a mix of both. We also learned that there is a correlation between the type of the background music and the preferred alert. The background music that shared similar characteristics also have similar preferred alert. However, there are limitations to this study. We'll discuss some of them. In this study, we scored the sound design with 7 criteria. But how can we be sure they are relevant for determining a good or bad design? It turns out that the high score does not necessitate best sound. In future studies, we could investigate which properties matters more, how they influence one another, and thus have a more reliable assessment of the sound. Second, the participants anticipated the alert, which may influence the survey result. Another limitation is how the design is tied to a particular scenario. with a short object lifting duration. Some of the sound might become disturbing when extended over a longer period. Furthermore, it's limited to one object. Will the strategy work for multiple objects? Next, we would like to suggest some opportunities for future research. First is to replicate the study with a bigger sample size and a more realistic scenario, so that we can confirm the findings, and also to collect more undiscovered design strategies. Next, we could also explore silent gaps to attract attention. In this study, the participants were directed to design a sound alert, and the silent gaps option was neglected. Even so, several of the design utilized empty space by filtering out certain frequency ranges. Another suggestion is to find out sound alerts for scenario with multiple objects. And finally, we could consider to auto-tailor the alert to any kind of background music.
All right, that is all of the videos for today's session. I would like to invite 4 of the presenters. We have Rod, who are representing paper number 1, and Sandra, paper number 2, Kura, paper number 3, and Puspita, paper number 4. We had one questions before that has already been answered, but as this discussion is going, feel free to follow up and write your questions in the Q&A features here in this Zoom. I would like to start first by asking Rod from paper 1. I'm just wondering about your the conclusions with the themes, because it seems that also has been explicitly described that the themes came from a bottom-up approach. That is, the themes were gathered from the analysis of the interviews. For the future studies, what do you think about the use of the similar themes as a top-down approach for the next ones, or do you think a bottom-up approach will still be better for the next ones?
There we go. Can you hear me?
Yes.
Excellent. Yeah, I think it's got to be a sort of open-minded in certain ways. So we've defined these themes so we can look for them, obviously, when we're going through the next session of data. But I think we also have to have an open mind that there may well be things that we didn't come up in the pilot, because obviously it's just 2 people in the pilot, and we're going to interview more sound designers. So I think we have to have an open mind that there might be themes that come up that don't fit into the top-down analysis. So that's my answer to that, really.
Okay. And then other thing about the areas of improvements. So what are the focus was evaluating the design briefs, right? So what are the improvements that you think could be implemented for this design briefs? Because I cannot quite catch that in the paper. Okay, so it was more to see whether we were the design briefs obviously elicited information, which they did. Okay, so what we were looking for to improve is maybe our technique, which I think has been shown to improve. So we're not disturbing the sound designers. Okay, there's possibly things we haven't changed it much, but like think the orders or the what ifs, or if people are, so a what if question, which possibly didn't come through there. There's additional questions that we might ask if the person is struggling to design. So instead of saying, can you design the sound for this? Can you design the worst sound for this? So part of it is us getting experience, knowing when we should intervene and sort of stimulate more discussion and more thoughts from the sound designer as they're progressing through it. And other times it's knowing exactly when to be quiet and just let them flow, because the information coming out is really invaluable. So I think we did manage that. We've defined our themes. We've seen that the themes have got this information. Now we just have to activate that, put it forward, and then start looking at, well, what are the techniques that people are using, and then build on these ideas. If that makes sense. Yeah, that makes sense. Thank you very much. I will get back to you if we have some more time later on. We have, I will just continue with questions for paper number 2 to Sandra. I'm curious about the use of physical interfaces for the digital sound model, because it seems to me, just like from the surface, it would kind of defeat the purpose of having a digital model if it's also with a physical model as an interface is also required. What is your thoughts on that?
Oh, I don't know if I understand your question correctly, but obviously, if you have a digital model, obviously we can use it. I don't know if you mean. Obviously, we can use it. Let's say we built it in Pure Data, therefore we can play it through the Pure Data interface, for example, or a computer interface. But it's much more interesting, and the type of connections and mappings between much more complex or physical interfaces with the sound can produce much more possibly creative outcomes. So, for example, we ran this workshop at KMH, and it was really interesting to see what people came up with in terms of potential interfaces for this kind of sounds. And one example of a sketch was in maybe the second or third slide. You saw perhaps like a spiral with things sticking out. They could move up and down. Obviously, you could not see that from the sketch, but they described how they saw that. Could work, right? And we imagined this potential interface to be able to connect to a number of different sound models. So both, for example, the footsteps, so a sort of rhythmical kind of thing, but also perhaps to the squeaky and creaks if this different things sticking out from the spiral, you can bend them, or you can bend them together and stuff like that. So the potential, the creative potential that a physical object gives you in terms of how you manipulate things and then how you can map that to the sound is, I think, much more rich, or can be very rich creatively. And that's why we are trying to think of different kind of physical interfaces for the sound models. We don't intend necessarily to, while we start with the initial kind of realistic, plausible sound model, we intend to kind of disrupt it in many different ways when we attach this kind of very weird or different playful interfaces, and we extend the parameter ranges of the model and etc. So it's starting from something that has an history and a past and a context and etc. to create something quite new and quite different potentially, and creative, hopefully.
Okay, yeah, thank you so much. I think I understand what's your point with that. Thank you for your answers. I see a raised hand here, but I'm going to move on with paper number 3. There is a question in the Q&A. I can read briefly. Question number 1 to Kura. What methods did you use to generate slices or atoms of your sound corpus? And question number 2, you mentioned atoms from 500 milliseconds to 1,500 milliseconds, and how did you account to change in the spectrum over the course of an atom? And was the nearest neighbor map convincing for your ears? And question number 3, how did you feel about the general applicability of your descriptor set? Did you need to tweak it for different sound corpora? Kura, if you please.
Well, actually, these slices are just kind of sliced. There's kind of no windowing or kind of that's type of stuff going on. That's actually done in the concatenation phase. So nothing special there. About the different lengths of the atoms, actually most of those approaches don't take into account the changing kind of nature of the atom or the spectral content. So actually only the CSDCE kind of the extension takes this into account by kind of taking a snapshot of the atom at the beginning and at the end, and kind of matching the end of one atom to the beginning of the next one. So that's the only one that essentially does something about this. And about the nearest neighbor map, for the CSDC, it doesn't always sound too great, but the extension does give somewhat smoother results, but it still takes some kind of tweaking in the atom length. And the descriptor set, well, I have the set here, so it's the spectral slope, spectral spread, the centroid, pitch, loudness, and noisiness. And I do feel that these cover most of the kind of parameters that would perceivably change the timbre. Although weighting between those parameters would maybe enhance the results somewhat. And no, I actually didn't change those settings. Only settings that I may have changed or that I changed were the number of neighbors to consider nearest neighbors.
Okay, thank you so much, Kura, for the response. And thank you, Balint, for the questions. I am going to go now to the raised hand with University of Oslo. Someone wants to?
Yeah, that was me, if you can hear me. I just really wanted to test this since we're doing this hub-based thing. I thought I should also ask an oral question, but this was about the last paper about whether you also thought about doing some kind of sound analysis in shops beforehand, and or if this could be part of a kind of future strategy when it comes to enhancing kind of the soundscape in these shops.
Puspita, go ahead.
All right. The analysis or the evaluation that we're done, it's not actually based on a real shop scenario. It's based on the video and the scenario depicted in the video where someone lifted the hanger and put it back. So yeah, that's the limitations that have been discussed. That the sound designs that we have is actually tied to that particular scenario in a video, and it's not an actual realistic scenario in a shop. So of course, all the different elements in a store soundscape, for example, not only the sound of people walking around, but also the temperature and the ambience of the store itself, the interior design of the store could also influence the results. So probably in the future research, it would really be beneficial to try it in a realistic scenario. I hope that answers your question.
Yeah, great, thanks.
Thank you, Puspita. And I have a follow-up questions. That is also the questions being asked here in the Q&A. So what are the practical implications of this approach of what you presented? Do we need to pack shops with sensors, because it's tied to hanger, right? Maybe each of the hangers need to have sensors in every one of them. What are the vision of this implementation?
So first, to answer what are the practical implications of this approach, if I understood this question correctly, then what we're trying to do is to discourage the shoplifter from doing the crime even before they do the shoplifting, because when they're lifting the object that they wanted to steal, and then they will hear the sound and they will realize, oh, I'm being watched, and then being discouraged from doing it. And about the question on the way if we need sensors or is there anything less intrusive. I can think of one way, which is we can actually use CCTV that's already pretty much in most stores, I guess. And then we can just track the movement from the camera. But the hanger lifting scenario is just one sample of the action. One sample of the action that can be sonified into a sound alert, and we can use another different action such as walking around or another action.
Okay, thank you. So perhaps to others, but one of the ideas could also be from the analysis of videos. Was that what you were saying? Okay, thank you.
Yes.
Great. I see that UIO Hub raised hand. Is this still the same from before, or is this a new one?
Yeah, no, I just want to comment on that. I mean, I
Yes.
understand that this is a little bit perhaps out of the scope of your study, which is actually very interesting. I was wondering then, how can we discriminate or differentiate between people that are touching something just because they want to try it out, and people that are touching objects because they want to steal it? I mean, but you know, I know that there is no easy answer to this.
Yes, actually, in this case, we don't discriminate between the shoplifters and the regular shoppers. That's why some of the criteria are, it should be noticeable but not disturbing the experience, because we don't discriminate. And for shoplifters, which has the notice the difference and felt that they're being observed, but for regular shoppers, they probably will notice the sound. But since it shouldn't be disturbing for them, since it is in the design criteria that it shouldn't be disturbing. I hope that answers your question.
Do we have more questions for the presenters? We have 2 minutes left in this session. Okay, if there are no more questions, then I would like to thank all